So thank you to the chairman, and I've been listening to all the talks, or at least most of the talks online. Unfortunately, I couldn't join you guys. I'm sorry about that. But the talks so far have been fantastic. And my big thanks to Stefan and his team for putting together this excellent event, and also for the opportunity for me to give a talk. So I'll get on with the talk now. So it's titled Exploring COFs for Lightweight and Fast Charging Storage. So in our group, Advanced Porous Materials Lab in India, we are working on different classes of porous compounds like MOF, COF, and porous organic frameworks, COFs, and so on. And we find that MOFs are quite suited for gas separation and storage, while the COFs have a wide variety of application ranging from water splitting, electrocatalysis, and classical catalysis. And there's a very nice philosophy which was proposed by Professor Andy Cooper, and we follow that there are no single solvent that can solve all the problems. So for example, in terms of MOFs, we work with preparing what are called ultra microporous MOFs using single ligands so that it is kind of potentially easier to scale up. And we look at these MOFs for various CO2 capture applications in general. And you can see some of the ligands we use are shown here. These typically tend to form nice ultra microporous MOFs. And Professor Seda Keskin gave a very nice talk and concluded by saying that what are the parameters we should be following to see the performance of a porous MOF for specific gas separations. So one of the things we follow is the working capacity. And we typically find that for example, hydrogen purification or pre-combustion capture, a 10-to-1 bar pressure swing would be our attractive target. And the other parameter we look, which is a holistic parameter, is the parasitic energy, which is kind of something that we take a lot of help from Professor Tom Wu from University of Ottawa to calculate these things. So today's talk, however, will be on covalent organic frameworks. So it all started with this seminal paper from Professor Yagi's group, where they showed that you can make all organic polymer without any metals as crystalline materials with high degree of order. So it is fantastic because you can see, looking at this powder diffraction pattern, it is very easy for someone to kind of not look at it properly, thinking it is a semi-crystalline polymer or something, but it was very wonderful that they actually understood that these are not semi-crystalline polymers, but more of a almost 100% crystalline polymers. The next big landmark paper came from them when they actually got single crystal structure of this all organic polymers, which really opened up door for new applications and new structure property tuning. And also very recently, we see that even zeolitic structures can be constructed from covalent organic frameworks, which is going to now really revolutionize the space of gas separation and gas storage and potentially many other applications. So for us still, we look at the COF from a very simple design principle, where what we see a COF as is a cross-linking monomer connected by a linear linker, giving rise to a very ordered structure. And because of the pi stacking capability of these building units, you end up getting beautiful graphite-like structures which are polymeric, and the pore size and shape can be tuned by the choice of linkers or monomers, as you would like to call it. And this is a very simple structure, and this really gives you a chance for a wide range of functional tuning and so on. And this is what really attracts us. And I will draw your attention to another interesting thing. I'm showing you here a high resolution TEM image of a COF, and I am comparing it to a graphene. And you can see that there are a lot of similarity, by which there are few important statements we can say. One is that the COFs are kind of nanomaterials, very similar to graphenes. And also it's important to realize, even in this small, few flaky structures, there are several layers of this graphitic material buried, which is very interesting. And despite being like that, this very flaky nanomaterial is highly crystalline. And what is the advantage of having something highly crystalline? You end up getting what is called as a very ordered structure. For example, I'm comparing a nitrogen doping in a graphene with a COF. So if you want to dope a nitrogen into a graphene, typically what you do, you take a carbonaceous source like a paper or a textile, and you pyrolyze a nitrogen-rich small molecule, and then you get a doping, which is kind of, just excuse me, just 1 second, which is kind of going to be very random. And also you do not know what kind of chemical nitrogens are buried into your structure. Whereas in comparison, if you take a COF, you are going to form a stoichiometric combination of monomers, and you are going to get a very ordered structure, which means you know exactly the nature of your heteroatom, and also you are distributed in a very periodic fashion, which means their axis and site specificity is going to be very high. And this really excites us to look into COF as a very interesting material. And so one of the things we look for is for charge storage. And one key thing for charge storage is shown in this very simple diagram, where what you have is an electrolyte which decides a potential window of operation. And also you have chemical potential of anode and a cathode. Now you have to have these chemical potentials or the energy levels of the anode and the cathode match the electrolyte in a very precise manner to be able to get a very efficient charge storage. For example, if you have very if these energy levels are not exactly positioned, you may get what is called as a solid electrolyte interface, which is an irreversible chemical reaction by which you might increase the resistance of your charge storage device, which is very unacceptable. But at the same time, you do want some amount of the SEA layer to be able to provide a smooth transport of charges at the interface of electrode and electrolyte. And why this is important? Because in a COF, since it's a modular structure, you can tune your monomers electronics to really achieve this exact energy levels that match with the electrolyte. And you can also have a variety of choice of electrolytes by tuning the chemical potential of your COF-based anode or a cathode. Now, if you look at a general principle for making an anode, you find that a lot of covalent bonds, if it is present in your structure, which is decided by the electronegativity of the atoms that are forming the material, you get a poorly packed structure with a lot of covalent bonds, and they are more suited for an anode. This is why in a lithium-ion battery, graphite is suited as an anode. Whereas for a cathode, you need materials with strong ionic bonds, which form dense structures. And so essentially, if you have them very crystalline, then you're going to have high degree of site specificity, which is very important for the movement of ions in and out of the material and be able to find the exact sites of interaction. And another important parameter for charge storage is what is called as the specific capacity. And if you look at the expression for specific capacity, which is Q, it is charge stored per unit weight of the material. And here you can see the denominator is molecular weight, which means if I have a small molecular weight, by default, I can get very high capacity. And if you look at what are the kind of elements that would suit that, then you can see here very nicely, it has been already classified that you can have boron, carbon, nitrogen, oxygen, fluorine, kind of lightweight atoms. If they can form your anode, that will be very attractive. And for the cathode, you want titanium, manganese, iron, nickel, copper, because you need redox activity very specifically for the movement of ions. And for the ions itself, people have identified lithium, sodium, magnesium, aluminum, these type of lightweight ions are favorable. So given all this knowledge that is available in the literature, we really wanted to embark on using covalent organic frameworks as charge storage devices. And so what is the idea we want? We want to make what are called as super capacity, which what it is, see here is the cyclic voltammetry representation of what a battery's CV will look like. And this is the cyclic voltammetry of what a capacitor's CV will look like. But now if you combine both of these, you can get something like this. So what is this? You do have a redox active behavior. At the same time, you're having a lot of surface charge storage via electrostatic interactions. And here is the charge discharge curve of a material which will be something like this. You can see it is a combination of these two charge discharge curves, and you do have a very symmetrical curve, which is possible in potential. And why is this very good? Because if you have this pseudo capacitor, you can have what is called as a very good power density as well as energy density. Energy density is like running a long distance. Power density is running a short sprint. You want the advantage of both in a charge storage device, and you can do that by looking at what are called pseudo capacitors. So they will lie somewhere here in what is called as this dragon plot. Okay, and if you look at a typical COF-based charge storage device, here is an electronic measurement using a 4-probe measurement. What I'm showing you, you can see the neat COF, okay, an actual neat COF, which is a 2D COF. The conductivity is almost negligible. Now, if I want to make this COF useful as a charge storage device, I need to impart conductivity to this. And typically, how do I achieve it? I put conducting carbon in about 15 to 25%, and then immediately you can see the conductivity of the composite goes quite high. Okay, and you can see that reflect also in the electrochemical behavior of the composite. And you can see the composite electrochemical current is pretty high compared to the neat COF. But what is the problem with this? See, as I told you, a pseudo capacitor works on the principle of charge being stored into it, which means your COF is going to act like a sponge, which really absorbs all the ions under your applied potential. But for that sponge to work very well, two things. If you have electronic activity, it will work very well because it can really get charged negatively, which means it can attract a lot of oppositively charged ions into it. But at the same time, this carbon that we add is a dead material. This is having only electronic conductivity and no sponge-like behavior. So you ideally want to avoid this carbon, which is a dense material, which adds to no sponge-like behavior, and make a single material which is spongy as well as electronically active. And unfortunately, if you look at COF, they do have a big pore in the middle, which means you are not having a complete conjugation across the bonds all through the material. And this makes it very difficult with the COF. And here is what we did. We took a COF. It is not like you can use any COF because these capacitive studies are done in highly acidic medium, which means your COF should have high degree of stability. So considering this, instead of going for a simple imine COF, we have gone for an imide COF with cyclic rings. And this really gives chance of a high degree of stability under the demanding conditions. With that, you can see here, then what we do, to improve the electronic conductivity of this COF, we grow polypyrrole into the pores of the COF. And this is also having some design aspect to it. So the polypyrroles can exist in two forms. Either it can be a linear chain or it can be a cross-linked polymer. Only the linear chain form of the polypyrrole has high conductivity, I mean electronic conductivity. So we naturally identify that the narrow one-dimensional pores of the COF will favor the growth of linear polymer rather than a cross-linked polymer. And this is what we believe is happening. And you can see that this is the actual photograph of the COF and the polypyrrole loaded COF. And you can see the color has intensified, suggesting there is higher degree of conjugation in this material, which would mean a improved electronic conductivity. Do we see that? We want to see that in a minute. Before that, we also find that upon loading the polypyrrole, the COF's lattice itself contracts a little bit, which is counterintuitive in some sense, because you would expect it to swell, but the contraction potentially could be due to the fact that the interaction between the polypyrrole and the walls of the COF are pretty favorable, and they make them interact strongly and shrink a bit. And also we see that even after loading the polypyrrole, there is significant amount of porosity left in the material, which means the spongy behavior is potentially intact. And we also see that the material is quite stable. And from the TGA, we find that about 24% of polypyrrole could be loaded into this material. And here is the SCM image of the neat COF versus the polypyrrole loaded COF. And you can already start seeing the nano chains or the micro chains of the polypyrrole all over the COF. You can always argue whether it is inside the pore or outside the pore, but we go through a very thorough washing procedure using sockslit methods, which typically removes the polypyrrole chains, which will be staying outside, which is soluble in selected solvents. And here is the HRTM image of the polypyrrole loaded COF. And you can see that in addition to the COF flakes, there are features which are looking more fibrous, which which are likely to be the polypyrrole. And here is the SAED pattern, selected area diffraction pattern. And you can see in the COF case, we do see good crystallinity, but it does decrease to a more of a polycrystalline rings when it is treated with the polypyrrole. And then from the EDAX, we are also able to see there is considerable amount of iodine being found in the sample, and that is coming because the iodine is going to act as a charge balancing anion into the polypyrrole chain, and that is the iodine we are looking at, which is indirectly confirming that there is a good loading of this, and you can see the iodine is well spread in the elemental mapping. Now, the most important thing is the electronic conductivity. You see here, this is the conductivity of the neat COF, which is 10 power minus 7 Siemens per centimeter. And after we have loaded the polypyrrole into it, you can see that the conductivity has increased to 10 power minus 3 Siemens per centimeter, which is quite substantial. And then from a variable temperature conductivity measurement, we see that it keeps increasing steadily, but after 338 Kelvin, it starts to decrease again, which is a clear behavior of a semiconductor-like material. And that is something we expect from most of the COFs, and the polypyrrole loading does not convert it into a metallic, but keeps it more like a semiconductor. Now, what is happening at the electronic level? So from the cyclic voltammetry comparisons between the neat COF, which is the red one, and the blue one, which is the polypyrrole loaded COF, we can see the shift in the oxidation onset as well as the reduction onset. And the shift can be directly related to the HOMO-LUMO energy levels of these materials. And you can see it is decreasing, the LUMO level is decreasing and the HOMO level is increasing when we load the polypyrrole into the COF, and the band gap shows significant decrease from 2.16 electron volts down to 1.56 electron volts. And the same can be observed also from the UV visible spectra, where we calculate using the top plot the band gaps, and you can see the band gap of the neat COF is 2.25 electron volts, which comes down to 1.58 electron volts upon loading the electronically active polypyrrole chains. And importantly, the electrochemical activity. Here is the cyclic voltammetry of the neat COF shown in red color. And then we see the cyclic voltammetry behavior of the neat polypyrrole grown as a control in the green dotted CV. And then the comparison is with the blue cyclic voltammetry curve, which is for the composite material. And you can see there's a drastic enhancement in the current of this composite, which is potentially due to the strong interaction between the both. So what is going on? If I have a neat COF, I'm storing the charge in terms of protons at the nitrogen centers or at the keto units and so on. But now, if I load the polypyrrole, in addition to the existing heteroatoms, I am bringing more heteroatoms which are protonatable. And once they are protonated, they can also bring in the iodide, polyiodide ions, as well as sulfate ions from the electrolyte medium. And this is very important because if you look at the energy density equation, you have charge capacity multiplied by the voltage window that directly tells you what is the energy density of your charge storage. And you want a very high value here, which means if you have a high charge capacity, then the material is likely to give you high energy density, and power density is nothing but a function of time. So one important thing is we want to expand this potential window for this material beyond 0.8 volts, which means when the voltage goes much higher, your energy density can be enhanced. Can we do this with this composite material? So before I go to that, we can also see from the 3 electrode measurements, there's a true capacitative behavior from the variable scan rates. And also you can see there's a strong enhancement in the capacitance when you go from the neat COF to the composite material. And the enhancement is almost 10 folds. But we need to show this in a 2-probe device, which is actually the working device, which we have made using this as a symmetrical capacitor. And you can see even upon flexing this device, still the cyclic voltammetry is completely intact, which shows the mechanical strength of this device. And the enhancement is seen also in the solid state device. So again, we compare the charge storage characteristics of the solid state device in the 2-probe measurement, and you can see the enhancement is very evidently seen, and the stability of the device is quite good. 82% of the charge storage is completely retained over a period of 6,000 cycles, and which is very interesting. And our material stands pretty good in terms of what is the area of capacitance observed for this material. You can see that this is the area of capacitance of our material, which is somewhere around 358 millifarads per centimeter square. We were very excited by this, but there is a problem. This material, again, even in the solid state, they can work only up to 0.8 volts or something. So if you want to expand beyond this, you now need to look at the electrolyte window, something I showed you at the beginning. So can we expand the electrolyte window and go to a higher potential? Yes, we can do that. This is where we joined hands with Professor Stefan Kaskel. These are the PhD student and master student from their group, and Satvik, who is a postdoc with Stefan, he conducted this study along with them. So what we have gone on to do is we have used ionic liquids as the electrolytes now. And ionic liquids can give you a much higher stability to your applied potential, which means you can start investigating a wider potential window. And we chose two different ionic liquids. One is less viscous, one is highly viscous. And immediately we saw that the less viscous ionic liquid is able to give you less resistance compared to the bulky ionic liquid. So we stuck to this for the most of the measurements. And what did we get? Yes, we could see that we could expand the potential window beyond 0.8 volts, and we could go all the way up to 2 volts. And naturally, we have expanded this potential window. And we also got excellent specific capacity for this material. Put together in the charge storage, you can see, you're able to see 275 millifarads per centimeter squared of capacitance coming from an all solid state material. This is not a gel electrolyte. This is a solid state electrolyte. Okay, and you can see when we translate this capacitance into the energy density, we are able to get excellent energy density and simultaneously very high power density. And this is exactly what was our target. So if you look at this, we are essentially now sitting here. This is the this is where we are sitting at the energy density, and this is where we are sitting at the power density. So we are exactly reaching this corner of the Ragon plot, which makes your material behave more like a supercapacitor, which is like a combination of supercapacitor plus a battery. So we then did a quick computational modeling, and then we tried to see what is happening at the electronic level in this material. So here is the HOMO-LUMO states of the COF, and you can see the LUMO is residing at the imide units, which is non-aromatic, and the HOMO is residing at the rich nitrogen centers of the material. But when I load the polypyrrole, what happens is the LUMO remains the same, but the HOMO is now residing more towards the polypyrrole, which seems to be very electron rich. And this now could be what could be the reason why you are getting very high electronic conductivity and thereby a superior charge storage. But there is always a question you can ask. They are not bonded, so are they really interacting? And the answer for this comes from literature, that there are so many cases where polypyrrole has been grown into MOFs and other structures where it has really shown to have an impact even when it is confined in a nano environment, to be able to interact with the host material to improve the electronic conductivity. So in summary, what have we done? Say I have a current collector on which my COF is coated. Now I want to transfer the electron from the current collector to the COF, for which you need very good electronic conductivity at the COF site. And you can see it is not very great because of the large pores. Now, if a polypyrrole chains into it, you can see that now a conducting COF is able to take the electrons very well, which means it will get highly negatively charged under an applied potential, which means the ions which are in the electrolyte, more of them can get absorbed onto the electrode now, which is exactly what is a charge storage. And this is what is reflected in the actual numbers. You can see the conductivity goes from 10 power minus 7 Siemens per centimeter to 10 power minus 3 Siemens per centimeter. Accordingly, the energy density and the power density, even in a solid state, is jumping to quite high values. So I think we have a very nice conceptual idea here, but we wouldn't say that we have obtained optimization. There's a lot of work still to be done. And it is not just us. There are a lot of interesting groups and very active groups who are working on anodes, cathodes, and capacitors based on COFs. And I would say that we need to thank all of these people for their continuous contribution, because that is what helps us look at different directions and go in the right direction for our kind of materials. So I would like to also acknowledge all the people who have helped me in this, and particularly this work was mostly done by Satvik, who was a PhD student with me, and he is a postdoc with Stefan right now, and then Deepak Rase, who is a PhD student with me right now. They did most of the work which I talked about today. And then I would also like to thank all my international collaborators who have been a big help in helping me get deep insights and also in being able to do complementary experiments for these kind of studies. And I thank all the funding agencies who have helped me with unlimited funds, I should say. And then I thank you all for your kind attention. And this is how ISER Pune looks on a beautiful sunny day. And so you are all welcome to join us. And even winter here is sunny, but not very hot. So please join us anytime you like, and I will be very happy to host you. And being an associate editor of chemistry materials, it becomes my duty to tell you that we have a lot of virtual issues coming on materials, and especially charge storage materials. So you are welcome to submit your papers to us, and you can see our impact factor has gone up beyond the magical number 10. So, and also our domain of materials is expanding every day. So with that, I would stop my talk. Thank you for your kind attention. I'm very sorry if you had exceeded the time. I'm open for questions now. Thank you.
Thank you. So any questions from the audience? If you have questions, you can just go to the microphone. Ramanathan, can you hear me?
Yes, very well.
Yes. Can I ask a question?
Please do.
Yeah. In your COF project, you mentioned that this is a solid state electrolyte, right? Instead of gel.
Yeah.
So I understand that there's a big difference between the two. And why do you think the solid state electrolyte is so important?
Sure. That's a very important question, I would say. See, two things. One is the safety and the prolonged life, okay? Because most of these liquid phase electrolytes, one of the key problems you would find is that it kind of can volatilize or can dry out, creating cracks and stuff on the surface, as well as when it dries out, naturally your performance starts to drop, and which is a key problem with the liquid state electrolytes. At the same time, for the solid state electrolytes, the diffusion of the ions is the biggest challenge. So if you can make highly diffusing solid state electrolytes, combine it with these materials, you really have a good chance of a very safe and long life battery with good energy density and potentially power density.
Thank you very much.